equal to 0 mod p, since they're both equal to y, which you can actually factor. So that would mean that you have x minus x prime times x plus x prime is equal to 0 mod p, which means that either, basically by the same logic we used up here, where p would have to divide 2x, that means that p would have to divide x minus x prime and or x plus x prime. And so that means that either x is congruent to x prime mod p, or x is congruent to negative x prime mod p. Since the definition of this congruency mod p is that p would then divide x minus x prime, or some number. So that is the end. We've shown that it can only possibly be x or negative x as our square roots. And so that means there's exactly 2 square roots. Oh yeah. So there's just a little picture of what z mod p star is. And then, so basically from understanding that, we have a few results. That means that exactly half of the elements of prime modulus are quadratic residues. And that means that we can write that the number of quadratic residues is equal to the number of quadratic non-residues, which is equal to the size of z mod p star over 2, which is equal to p minus 1 over 2. So we have basically an amount for however many quadratic residues there are in a certain prime modulus. But since we're talking about c mod p star, it's important to note that it has a certain property. We're going to look at c mod 19. So basically, 19 is prime. And since it's a prime group, you can apply a certain property to it, where you choose an element, a certain element, and by raising that element to successive powers, from 0 all the way up to p minus 2, you can actually just get every single other element in the group. So I basically just colored everything so that you could sort of see that each color is represented is exactly once in the top row and once in the bottom row. And you generate these values just by raising this generator element, which for z mod 19 star you have 2 as a generator. And you can get everything else except for the numbers that are congruent to 0 because they're not included. So that's pretty wild. And you can, are there any questions right now?
Okay, so do you mean that there is some kind of a cycle the powers go through, right? So
right.
at 2 in the power of 18, what would be the residue?
At 2 to the power of 18,
Mm-hmm.
you would just get 1.
Yeah, I see. Yeah, we would just get 1, right? So it's basically like a cycle, right? That you go through. The cycle would have like 18 steps, and each 18 steps will just come to the same powers.
Yeah.
And you're using 2 because it's a main kind of computer science number.
It's a good number. Pretty easy to see.
Wait, if you pick a number other than 2, you'll still get the same phenomenon where
Yes.
all of them are
But p
only
has to be
used once?
prime.
Okay.
I mean, it's not guaranteed that every single one, I'm actually not sure if every single one will do it, but there's at least one that will definitely do it.
The p in this case is 19, so that number always has to be prime. But the 2, that number that you pick doesn't have to be prime, right?
I'm not sure. I can Google it.
Okay.
I think I actually should.
Yeah.
Yeah.
I mean, it shouldn't. Definitely shouldn't be like.
Yeah, I think I can show you after this how do you do that. But yeah, that's further.
Okay. Wait, is that the same? Oh, okay. So now we're going to square everything to calculate the quadratic residues. So as you can see, half of them are the half of them are the same as the other half, and this cycle repeats exactly at the end. So by squaring the generators that you have, you can actually split it directly in half, so that if you reduce modulo p minus 1 in the exponent, you're going to get the exact same thing as before. So like 2 to the 0 is the same as 2 to the 18, and so on. And that's because of what, like you said, like it's a cycle. So if you double the cycle and just like skip